Welcome everybody. This is our video solution to problem 4 from Superquiz 3. This problem is about showing or computing the radius and interval of convergence for a given power series. And what I would like to do from the beginning, though, is just kind of ignore this radius and interval of convergence bit and just say, okay, I want to show that the series converges or diverges, right? I'm just going to use one of the usual tests. And of course, the answer is going to depend very much on what the value of x is. So eventually that's where this radius and interval of convergence is going to come from. But in the short run, I'm not going to worry about all that jazz. Okay, now, when you're working with power series, it's pretty typical that you'd like to use either the ratio or the root test. I personally prefer the root test because it's going to kill this n pretty nicely. And I have some good heuristic rules for dealing with whatever the coefficients of the power series are. So I'm going to start with the root test, but I'll also do it with the ratio test. And it's really not that hard with the ratio test here either. So with the root test, we need to take the limit as n goes to infinity of the nth root of the absolute value of 3n to the fourth plus 1 over n to the fourth plus 1 times the nth power of x plus 2. Now, the absolute value of a product or of a quotient is just the product or quotient of the absolute values, and the same works with the nth root. So I can break this limit up as the nth root of the absolute value of each of these individual factors. Now, the first two, 3n to the fourth plus 1 and n to the fourth plus 1, are always positive, so I'm going to get to drop the absolute value there. But this x plus 2 to the n, that actually could be negative, so I'm going to have to worry about that absolute value. So I'll get the nth root of 3n to the fourth plus 1 over the nth root of n to the fourth plus 1 times the nth root of the absolute value of x plus 2, and then I take the nth power, right? Again, absolute value commutes with product, so I can pull out this exponent. Now, let me look at this third factor first, because that's the easiest one. The nth root of x plus 2's absolute value to the n is just going to be the absolute value of x plus 2. And you'll notice this doesn't have any n in it. It's a constant with respect to n. So I'll be able to pull the absolute value of x plus 2 out of the limit. And now I'm just left with the nth root of 3n to the fourth plus 1 over the nth root of n to the fourth plus 1. Now I've given some heuristics in class, and one of them is that the limit as n goes to infinity of the nth root of n to the p is equal to 1. And so if you include extra stuff under this radical that are just powers of n, say, right? And they have smaller powers of p, then as n goes to infinity, those won't be as significant. Okay, so we should expect each of these to also be going to, for example, this n to the fourth plus 1, we should expect that also to be going to 1. And okay, you might say, oh, this 3, that might do a little something special, but not really. I mean, that's actually a special case here or actually, we did another heuristic. Let me write down the other heuristic, which is just if you have the nth root of a constant, the limit is also going to be 1. So none of that should matter. Now, I haven't really given a proof that it works when you use smaller terms under this radical. So let me just do a quick argument there. So let me say y was going to equal the limit as n goes to infinity of the nth root of, and let me just do kind of a more general statement here. I'll have some constant times n to the p, and okay, let's just add a constant. And other arguments are going to work very similar to this one. So what I want to do here is I want to take the natural log of both sides. And because the natural log is a continuous function, it's going to commute with this limit. So I can pull the limit outside and put inside the natural log of the nth root of a times n to the p plus b. Now, an nth root is the same as raising to the 1 over n power. So this piece in here is the same as the 1 over nth power of an to the p plus b. And the reason I want to write it in this alternative form is because we know that the natural log of an element to a power can be rewritten as the power times the natural log of the element. So I'm going to be able to rewrite this limit again as 1 over n times the natural log of an to the p plus b. Now, this is a limit that has to do with sequences, right? N is just some discrete value, but there is a generating function for this. Okay, so I'm going to look at the function f of x equals 1 over x times the natural log of ax to the p plus b. And if I take the limit as x goes to infinity of this now continuous function, in fact, it's even differentiable, I'm going to be able to use L'Hopital's rule, right? Because I'm going to rewrite this as the ln of ax to the p plus b over x. And as x goes to infinity, ln of ax to the p plus b is going to infinity, so is x. Okay, or I should have said here, of course, we're assuming that p is some positive constant. So when I apply L'Hopital's rule, I keep the limit. I need to take the derivative of the top and bottom. Now, the derivative of the bottom is 1. So that's going to go away for us. So derivative of a natural log function is going to be, okay, we take the derivative of the inside. That'll be p ax to the p minus 1 over the actual function, ax to the p plus b. And this is a situation we've seen a lot before in class where we have here just a power of x with a constant. We have another power of x on the bottom, but this power of x is larger than the one on the top. And so we should expect that this limit is going to be 0. Right? Now we can show it again easily. We're going to just divide the top and the bottom by x to the p minus 1. So when I do that, on the top, I'm going to get p times a. On the bottom, I will get ax plus b over x to the p minus 1. And as x goes to infinity, this piece goes to 0. This piece on the top is a constant, but then this ax is going to either go to plus infinity or minus infinity, depending on the value of a. And so this limit is going to be 0. Okay, and so this tells us that the limit with just n is also going to be 0. But this limit was equal to ln of y. And so ln of y is equal to 0. And so exponentiating both sides, we get y is equal to 1. Okay, so that's how we can verify this, this set of rules and extensions of these rules for nth roots, right? Which is going to be really useful for the root test. So each of these pieces is going to go to 1. And so the limit is actually just the absolute value of x plus 2. All right, now the root test says that we get series convergence when this ratio that we got, right, or that rather this root that we got is less than 1, and we get divergence when it's greater than 1. So the series 3n to the fourth plus 1 over n to the fourth plus 1, x plus 2 to the n, converges for absolute value of x plus 2 less than 1, and diverges for absolute value of x plus 2 greater than 1. There we go. Okay, of course, there's still this missing case in the middle that we're going to have to look at. What happens if this is equal to 1? But before we do that, let's draw a little picture, see when these sort of things happen. So remember, anytime you write down the absolute value of x minus a, this means the distance between x and a. And if you write down the absolute value of x plus a, well, we could rewrite this as the absolute value of the difference between x and negative a. And so this would be the distance between x and negative a. So we have absolute value of x plus 2, so this means the distance between x and negative 2. So let me plot negative 2 on this chart. And we're saying that the distance needs to be less than 1. Okay, so 1 away would be a negative 1 and a negative 3. And so we know that we now have convergence anywhere the distance between x and negative 2 is less than 1, so between negative 3 and negative 1. So immediately, we're going to be able to write down that the interval of convergence is equal to negative 3 to negative 1. The only problem is we don't know whether to put rounded parentheses or square brackets on the end. The radius of convergence, though, we know exactly what it's going to be. It's going to be this number here, 1, right? That's the radius of this interval. So that's going to be a 1. So the only thing left we have to do is actually check these endpoints. Okay, so the endpoints are negative 3 and negative 1. So when x is equal to negative 3, let's see what our series becomes. So when x is negative 3, x plus 2 to the n becomes, let's see, negative 3 plus 2 is negative 1 to the n. And so our series will be, we get an alternator, and then 3n plus 4, 3n to the fourth plus 1 over n to the fourth plus 1. Now this looks like a good time to use maybe an alternating series test, because there's an alternator, right? Maybe not so fast. Let's take a look at this piece. If this piece doesn't converge to 0, then we have no hope whatsoever. And it's not going to converge to 0, because look at this. We have 3n to the fourth, and we have an n to the fourth. These are the same power of n. And we know then in the limit, this limit is going to be 3. Okay, it's the exact same sort of argument we were making over here. We'd factor out an n to the fourth. Okay, so this piece right here goes to 3 as n goes to infinity. Okay, now there is an alternator, but that just means that this thing is alternating between things close to 3 and things close to negative 3. And we know by the non-vanishing sequence test that we need the limit to be going to 0. And so this diverges by the non-vanishing sequence test. So we actually get to put a parenthesis on the end here. So our left side of the interval of convergence will have a parenthesis. And actually the same thing is going to happen for negative 1 as well. For negative 1, x plus 2 to the n is going to be negative 1 plus 2 to the n. That's just 1 to the n. And so our series, we have the exact same problem. There's no alternator anymore, but we still have an underlying sequence which is converging to 3. Right? So again, this converges to 3. So we get divergence by the non-vanishing sequence test. Okay, so we can come back up, put another parenthesis around our negative 1, and our interval of convergence will be negative 3 to negative 1. Whew, okay. I promised I would do the ratio test version, right? Now, if we do the ratio test, what I claim is going to happen is we're going to get the exact same condition out. So I'm not going to repeat the x equals negative 3 and the x equals negative 1 condition. So let's just see what happens in the first part of the test. So if I go to use the ratio test, then I'm going to be taking the limit as n goes to infinity of the absolute value of, all right, so I need to take the n plus first term. So it'll be 3 times n plus 1 to the fourth plus 1 over n plus 1 to the fourth plus 1 times x plus 2 to the n plus 1. And then we need to divide by the nth term or multiply by its reciprocal. So to multiply by the reciprocal, I am going to have n to the fourth plus 1 over 3n to the fourth plus 1. And then I'll have 1 over x plus 2 to the n. And we'll close our absolute values. Okay, and you can see this is going to work okay, but it's why I kind of like the root test here, is I don't have to work so hard to simplify these things. But there we go, we can do it. First thing, because this is the easy part, I have x plus 2 to the n plus 1 and x plus 2 to the n. So there's n plus 1 copies of x plus 2. I divide by n copies of x plus 2. And so I'm just left with 1 copy of x plus 2. And in fact, let me just pull that all the way out with an absolute value. Okay, again, it has no n, so it's a constant as far as the limit is concerned. All right, now what about the rest of this junk? Whew, okay, so we have, I don't need absolute values anymore because everything else is positive. I have 3 times n plus 1 to the 4th plus 1 times n to the 4th plus 1 over n plus 1 to the 4th plus 1 times 3n to the 4th plus 1. Whew, okay. One can try to multiply this all out, and it's going to just be garbage, okay? The important thing here is to remember in these situations, it's only the highest power of n that we care about. So let me write this down again. And we're going to expand, but just enough to see the highest power. So as I start to distribute, I'm only going to worry about the highest power. So for example here, I have n plus 1 to the 4th power. And when I distribute this, the very first term will be an n to the 4th. Then I'll multiply by 3, and I'll have 3n to the 4th. And then I have to multiply by this guy, and the biggest thing I'll get is multiplying by n to the 4th. So the biggest thing I'll have is this 3n to the 8th power. After that, I'm going to get a bunch of other junk, and it's all going to be smaller powers of n. So I'm going to use, first, I'm just going to say lower order powers of n. Okay, just so you understand, that's what I'm getting at, right? It's just lower order stuff. Okay, and then on the bottom, here again, I have an n to the 4th and more stuff, but I'm going to multiply by a 3n to the 4th, so I'll end up with a 3n to the 8th, and again, plus lower order powers of n. Now, it feels kind of gross writing down lower order powers of n all over the place, so let me just quickly introduce a little bit of notation. And I don't want to, in this video, go through all of the definitions for this thing, but I just want you to get an intuitive sense of what it means, and maybe we'll come back with another video later. So I have 3n to the 8th, and instead of writing down lower order powers of n, I'm going to write down big O of n to the 7th. And you can treat this as saying I'm going to have some expression which basically grows no faster than n to the 7th. And on the bottom, I have the same thing, 3n to the 8th plus big O of n to the 7th. And for the purposes of what we're doing here, we know we could factor out an n to the 8th from everything. And anything which grows no bigger than n to the 7th is going to go to 0 when you divide by n to the 8th. Okay? Just like if you took n to the 7th and divided by n to the 8th, you get 1 over n. As n goes to infinity, that limit will be 0. So in this case, we only care about the highest powers. And because n to the 8th and n to the 8th are in the top and the bottom, we just care about the ratio of their coefficients, which is actually 3 over 3 or 1. So this entire limit is just going to equal 1. And so we end up with the absolute value of x plus 2. And so once again, right, by the ratio test, the original series converges if the absolute value of x plus 2 is less than 1, diverges if the absolute value of x plus 2 is greater than 1. And again, in the x plus 2 absolute value is equal to 1, we've handled those cases already. So we'll get the same answer in this way. All right, but that's how we can use the ratio test. It is pretty useful being able to use this notation when you're handling these limits, right? Once you get the idea that all you care about is the highest order terms, then it's nice to be able to just collect all the rest of the stuff because you don't want to write it down because it doesn't even matter, right? It's all going to be garbage anyway. All right, take care, everybody. See you next time.